Kiko?
Hi, Dr. Schmidt.
Everybody doing okay?
Dr. Schmidt, do we have a 3-day weekend?
Sure.
Was that real, Diana? In class? Did you hear Mr. Keeverly?
Oh, yeah, that's a real thing.
Oh yeah.
Is it really?
Yeah.
It's not a joke.
No, you're kidding. Okay. No, I have Blue Fridays off anyway, so I would have had a 4-day weekend.
I almost have Blue Fridays off. I have one class.
Like every day is just a more busy day of break, it feels like, since we're at home though.
Yeah. No, we don't have class on Monday.
Does that mean there's going to be only one evening class that week then?
Yep.
Okay.
Yep, on Thursday.
So, yeah. Long weekend. Wow.
Yeah, I mean, enjoy staying in your room and
They'll take a longer walk than usual or something. I don't know.
oh, let's not get crazy.
Yeah.
Well, let's see. Anybody have any fun plans for their long weekend? So many?
I'm grinding Mario Kart.
Mario Kart. Okay.
Might try to reattempt a project we did in 8th grade physical science with like stacking water with different salinity levels on top to make like different, almost like a
right.
rainbow test tube and try to get more colors.
No, you just have to be really careful when you add the other liquid. And you can, if you're very, very careful and try not to disturb the surface too much as you're adding the second liquid, then it will work.
Mhm. Yeah. I was experimenting a little bit last merge break, and I think I got like a fairly good amount of colors. I figured out some sort of good like amounts for the measurements, but I forget exactly what it was. I wrote it down like a napkin, so try that again.
Yeah, this time period here while we're waiting for everybody is like my least favorite part of online classes. It makes me really sad.
So we should introduce like waiting room games. Is that like tic-tac-toe or something? I don't know.
I could immediately assign you all to a little breakout room,
Oh yeah,
right?
yeah.
And
It
then,
has like tables.
yeah, it's just like tables.
That would
And then
actually
you,
be really fun.
hmm?
That would actually be really fun.
Yeah.
Yeah.
Okay. I'll try to do that.
Yeah, we should do that for 10 minutes right now.
Not right now. But I will try to remember to do that next time. Or if somebody reminds me, that would be helpful too. All right, I think we have almost everybody. Let's see, June. Oh, there he is. And Maya. Oh, Maya's here. Sexy. I think everybody's here. All right. Couple of things of note. We have no class on Monday because it's long weekend. So, enjoy the day off. Maybe sleep in. Maybe stay in your pajamas all day. Maybe you don't have to dress up in dress code. So it'll definitely be a welcome relief to your normal everyday activities. So that's good. And our next class is on Thursday, the 30th. Okay. As I've received a few people who've started their projects for passing with honors, and that's great. I just want to encourage you to not do too much for this. Once you think that you've got about 2 pages worth of stuff, just stop there. You don't have to think that you have to completely understand this new topic that you've picked. Okay. Because I think that would be a lot of work. And I'm not intending for it to be a ton of work. Okay. All right. So I wanted to try out this polling feature here. So I'd like to see how far people got on their homework. So I'm going to try to give you folks a poll. Who says that I can do this? Okay, 100% participation. All right, looks like people got pretty far. And the vast majority of people finished it. Or at least got through question 9. All right, so that's great. I thought we would spend some time going over the first page. The first page is basically calculations and making sure that you use those calculations correctly. So it's a good idea to double check all of our calculations, make sure that we're doing this skill correctly. So we're going to get into smaller groups and check over our work on the first page. Okay. Okay, Maya.
$167,210.
I got 979,000.
I got 967,901.
I think it's just how we rounded converting 70 miles per hour to meters per second.
Yeah, there's not a significant difference between 969,000 and 971,000.
Okay.
There is a significant difference if you get like 30,000.
Yeah.
So everybody got around in the high 900,000s.
Yeah.
Okay.
All right. Number 2. Oh, my OneNote crashed. Dang. It's just converting the calories into joules.
Yeah.
By the by the amount of joules in 1 calorie.
Yeah.
So yeah.
I got like 753,000.
Yeah. That too.
Mm-hmm.
For A, did you guys get 0?
Yeah, because
Yeah.
I said it like it's the distance from the reference point, and if it's at the reference point, it's just 0.
Yeah.
And then
And
20
for-
point, yeah.
Yeah, 20.4.
And
Yep.
then you have 75.
Negative, right?
Yeah, because it's
Yeah.
Below it.
Yep. And then
Any questions so far?
no.
So far.
Okay.
It wasn't. All right.
Wait, how many was it?
Should I stop screen sharing?
Uh,
So you know this white writing on the black background? I can't see it when I look at my.
Yeah. You have to make it gray or
How about
something.
that? Yeah, I'll just select all of it.
So I mean, it's fine as long as you don't expect me to look at it.
No, that was my work. So you need to see my work. I'll do red. There we
Oh,
go.
there you go.
Just set that as my default font, like color.
Right.
Okay. Yeah, I get it. My only mistake was I forgot to do stuff with like the hours and then convert it to seconds. But that's okay. I think I did everything else all right. I think you're good too, Mason. So number 2. I was kind of confused on number 2 as well. What did you guys get?
I just multiply the two numbers.
Yeah.
I get 35,340.
Wait, 7.
Wait, what?
What'd you
Number
say?
2? How
Yeah,
much?
no.
Yeah.
What was your end answer?
What? Can't hear
What
you.
was your final answer?
My final answer was 35,340J for number 2. Because it's just saying how much energy does. It's 180 calories and said 1 calorie is this many joules. So I just did that many
Wait,
joules.
so did you?
I got 753,000.
Yeah,
Yeah,
that's
I
what,
got that as well.
But how
Because
you get?
180 times 4,186.
Oh, I think I used the wrong number.
oh, you probably did.
There were only
I don't
two
know where I got
numbers.
these two numbers from. I used completely wrong numbers.
Yeah, that's probably what happened.
Okay.
Okay.
Okay, it happens.
Yeah, that one's not that bad.
Right, fix it.
All
Yeah,
right.
so
I don't
7.
think I got a single 100% on any test in high school. I always make mistakes.
ELF. Okay, so it's 1/2, 3.33, and then that's 0.01, right? No, that's 0.1, 0.1, 0.1, right. Squared.
Yeah.
And then EEL equals to, I don't want to do the calculation, so I'll just copy your 166, okay. Wait, how many sixes?
3. Or there's 4, but it's 1,666.67.
Julio.
All right,
I'm
you're
good.
fine. I mean, you could round to
I know.
1,700. That would be fine. Austin, just note that you are being a little sloppy with your units. You forgot them in a couple places.
Oh, Abby.
And can you scroll up slightly so I can check number 1? Yeah, it looks fine. Different people are going to get slightly different answers on number 1 depending on how they round.
Yeah, I got a bit of a different answer.
I got 973,440.
I got 967,901.23 joules.
Yeah.
Okay, I was a bit confused about the qualitative energy conservation equation because I just did, well, or that's in number 7.
Number
Correct?
7.
Oh
yeah.
I had to do, so it has to be quantitative, so you have to have numbers. But
Oh, it's quantitative. Oh.
yeah, if you plug in like the mass and the velocity, then you'll just get the answer. So I didn't plug those in. I just did 1/2 mass times velocity squared is equal to 1/2 k times change in x squared. And I guess that is quantitative, but it's just like, it's just variables though, so it confused me. I didn't know if that was right. So
Yeah, I don't think I ever noticed that it's that quantitative before.
oh really?
Should we?
Um, but it's fine. But I think it's saying it wants a little bit more work here.
Okay.
So somewhere, well, I don't know. We'll look at it. Here, I don't think you're really showing. At C, I'm not sure where these numbers are coming from. Austin, why 75 nm divided by 50?
Oh,
Yeah, I didn't seem to have the same answer.
Okay. So you're saying that the elastic force is 75 Newton meters?
I'll redo this.
Okay.
Because I just kind of made up numbers
So the first equation that you write, the energy conservation equation, should help you to figure out the problem.
Right, yeah, because I know that I didn't know how much to like, but the thing is like when in terms of like dissipation and stuff like that, like how much energy is being dissipated, I didn't know exactly like how much I should have.
Oh yeah, is there energy dissipated from the crash? I was a bit confused about that, like the crash against the spring. Because I said that there wasn't, but then I remember when we did it before in class, when the cart crashed, it had dissipated energy. So I just didn't know.
Or could you like
I'm
make
circling
it up for
something in the description.
Well,
oh, I just circled it too.
Oh, so no friction? Yeah.
Nice. That's better for all of us.
Yeah.
Makes it a lot easier. So remember how I said we'd probably start ignoring friction because it makes the calculations possible?
Mm-hmm.
That's what we're doing now. Just like we would ignore air resistance because we couldn't calculate it.
Right.
So now we're going to ignore friction because we don't have any good way of calculating how much energy is lost to dissipation. Yeah, I need to make sure everybody's doing okay on the first page. We'll come back to this.
Okay.
Okay, cool.
Okay, how's the first page looking?
Good. We all got the same things.
Okay. Can I see so I can double check that nobody did anything silly?
Yeah.
I can share my screen.
You made a mistake in number 6.
Okay.
But it's probably just putting it into your calculator wrong. It's easy to put in the wrong number of 3s, for example.
Yeah. I had too many sixes.
Okay. And it is absolutely fine to roll. So a good rule of thumb is that you look at your problem, okay, and you see how there's 2 digits here.
Mhm.
Your answer doesn't have to have any more than 2 digits. So you could round to 1700 joules, just fine,
Okay.
or even 1670. You don't have to go 6 1 6 6 6 6 6 6 6. Okay.
Yeah.
All right. Yeah, this is looking pretty good. If you wouldn't mind sharing your screen to the whole class so everybody can double check just in case somebody missed something. I'm gonna bring us back together and double check this page, and then we'll move on to the next question.
Okay.
Okay. Always somebody who gets stuck. All right, Diana volunteered to show her answers to the first page, so we can all double check. But I saw the work I saw looks pretty good in general. I didn't see a lot to comment about.
So for the first page, we used the kinetic energy equation, and we plugged in 2000 for the mass. And then I just directly plugged in well, first you had to convert the 70 miles per hour into meters per second. So I did this little, whatever it's called, I'm kind of forgetting the name, ratio. So then I got 112,000 over 3,600, and then I got my kinetic energy.
So different people round that step a little bit differently, but as long as you're getting close to 970,000 joules, you're on the right track. If we scroll down a little bit, number 2, I didn't see people having too much trouble with unless they had a calculator issue or something like that. 3 also is pretty straightforward. The one thing I sometimes see is that people don't make 3C negative. Right? But it is underneath our reference point. If our reference point is up here, then our book is underneath it. So in order to get to that amount of energy, we'd have to put energy into it. So it's kind of a deficit of energy. Okay, so it does have a negative amount of energy. If you think about energy like money, it's quite possible to have a negative amount of money, sadly. Again, just calculations. Just look them over really quick. You can see if you have any issues, or if you see you can figure out what you did wrong. But I think everybody was pretty much on the right track. There were just some inputs into the calculator wrong and things like that. Does anybody have any questions on anything? On number 6, it's really important to convert your units correctly. Okay. So we'll get back into our groups and we'll start discussing 7 and 8 and maybe 9 if you get to that.
So I guess I plugged that. I just did it and I left the mass. Like I didn't put a number for mass. I just left it as a variable, right?
Are we now already doing number 9?
Yes.
Yeah, we went over 7 and 8 during the last time.
Okay.
Yep. And when I plug that into the kinetic equation, right? So you just get 15 newtons times the mass equals the equation, right? So 1/2 times mass times velocity squared. And then you can divide by mass and just get 50 equals 1/2 of velocity squared. Oh, okay.
Yeah,
And I kind of got confused at the end because it said that we lost 10% friction. And I didn't know if that meant at the end or at the beginning, or I just didn't really know what it meant. So I just kind of took 10% off velocity.
So I'd encourage you to make a energy conservation equation like we've been doing. All right, so that's probably a good place to start.
Okay. Just say like, can you just say something like that?
Okay. So I would, so where's the 0.9 coming from?
The 10% loss to friction.
So 0.9 times EK plus,
Oh, my bad, yeah.
0.1 times energy dissipated.
Wouldn't it just be energy dissipated? Because that's 0.1, not 0.1.
Right, right. Okay. So I'm not sure that I'm still trying to figure out where the 0.9 goes. Why is it 0.9 times EK?
What do you mean 0.9 times EK? It's the energy kinetic, right?
Yeah, why is that
So
times
it's
0.9?
not. It says that you're assuming a 10% loss to friction, so you're losing 10% of your energy when it goes from A to B. So EK is only 90% of EG. The other 10% is the thermal energy. I'm just.
So if we write in the blocks that you have here, you have like 5 blocks here, right? You put 5 blocks here for EG, right? And then you put 0.5 blocks over here for the thermal energy.
Yeah.
So, and then you put 4.5 blocks here.
Yeah, I'm thinking about it wrong. You're right. I don't have to do 0.9. That would be equal to something else.
So this statement seems absolutely correct. The gravitational energy is equal to the kinetic energy plus the thermal energy, right?
Yeah.
Are we all in agreement about that? Yeah. So now we just need to figure out how to set it up. So with this 10%.
Would it be EG minus thermal energy equals kinetic energy?
Oh, so there's an idea. So the EG minus the thermal energy equals the kinetic energy. Okay, and how does that help us?
Is it because like we know that the kinetic energy is 9/10 of the gravitational energy, so could we just we know what the thermal energy is if we just make it 1/10 of the gravitational energy?
Okay, so then I could replace thermal energy with 1/10 the gravitational energy. Like that.
But then what do you do? Do you just like how do you take out the how do you find the energy kinetic?
Over here, you figured out that the gravity energy was 50 M, right?
Yeah, 15 units times the mass, right?
So I can plug that in here. So then the gravity energy is 50 M minus 1/10 of the gravity energy, which is
0.05, 0.5. I don't know. 0.5 of mass.
5 M. What 1/10 of 50 M is 5 M.
I'm sorry, 5.
It's very early for Alan, everybody. He wakes up at like 6 o'clock every day.
Fine.
Just so you know.
My brain to work. So you would get like 45.
So you get 45 M is equal to the kinetic energy. Okay, and then you can take that 45 M and plug it in down over here where you plugged in 50 M.
Wait, what happened to the Newton times meter?
Oh, I left it out because it gets confusing at times because you don't always know if something is a unit or a mass. Like the M could either be mass or it could be meter.
Yeah.
Right? And so that can get pretty confusing. So I left out all of the units until the final calculation. But then the key thing here is that the mass cancels. Okay. So that's my general advice to you. It often happens in physics that the mass will cancel out. So the problem won't have any mass in it, and they'll be like, if we still had tests, I would have a steady stream of students coming up to me going, Dr. Schmidt, you didn't give me the mass here. And then I go, yep. Okay, because if you put in the mass as a variable, it will often cancel.
Okay.
Okay, great work. I need to check in with other people.
Thank you.
Thank you.
All right, number 10.
How are we doing here?
Good. We're good. We finished up. I ate breakfast. Can't complain.
Okay, what did you have for breakfast?
English muffin and some cereal and some watermelon.
Watermelon. Wow.
It was pretty good.
Who would like to show me their work?
Which one?
What do you want to look at?
Well, I'll glance at 7 and 8, but 9 is the trickiest one.
Can I give you my answer for 9? You shake your head or nod your head depending on how close I am.
Oh, that's all how you did it. There's elegant ways of solving number 9, and then there's kind of ugly ways. Both of them give you the right answer.
I got 10 meters per second. I don't know how close though.
Oh.
Was that ugly? Was it not ugly? Or was it just wrong?
Let's see. So if somebody, I know a lot of people have trouble sharing their screen, so you just tell me you wouldn't mind me looking at your homework, then I can share what you have.
I can share it. It doesn't. It works fine on mine.
Okay.
I don't really like putting up the wrong answer, but you know what? It's all right.
Yeah.
I started with.
Is this better or worse than putting up the wrong answer in class?
Oh, I don't know. Actually, here you don't like feel like everybody looking at you. You just see 4 people. So I guess
Yeah.
this.
Okay.
Anyway, my first.
So why don't you scroll up to number 7 and 8 so I can double check those really quick.
All right. Can you see the whole?
All right, that looks good.
That was what I did for 7.
Okay.
And for 8, I started over here and found the elastic energy, and then once I got that 4.5 joules, I brought that over here and used that to solve for what my gravity would be because I knew they were the same value.
Okay, excellent.
And
All
then
right.
9 kind of got off the rails, and 10 we were just not even on the track anymore.
Oh no. All right. So tell me about your approach to number 9.
So my first thought, now I'm thinking about it because there's the 10% lost. I think I need to multiply something by that 0.1 or whatever. So now I'm thinking I possibly take this 50 right here and multiply that by 0.1, and then that value will give me what I want to plug in here.
So you got through one of the trickiest parts, which is just to, you're not given the mass, right? But if you just plug in the mass as a variable and keep it around, it eventually cancels out, as you saw.
Yeah.
So that's one of the trickier parts. It doesn't tell you to do this, but it's still a really good idea to start with a energy conservation equation, like we've been doing. So let's go ahead and write that down and see if it helps us.
So it'd be like energy K. Would you say that's the dissipated energy, that like point, or the 10% loss?
Well, so you have your loss to friction, you have it stacked on top of your K. Is that where we have been putting it?
Nope. Yes, so just put it right here and just do like a little bit.
Okay. over to the left a little bit.
So maybe, would I multiply that 50 right here?
So I don't understand your LOL diagram. Right? Isn't the roller coaster up in the air? And doesn't it have a velocity of 0?
Oh, I think I wrote those in the wrong places. Yeah, so this would be the gravity, and then this would be the.
Okay. So that changes your equation a little bit, right?
Yeah.
All right, so now what would the, where does the 10% come in? So we're given a 10% loss to friction. How could we put that into our equation?
0.9.
Okay, where?
Like in the gravitational energy is 0.9 equal to the kinetic energy.
Okay.
Could you like 0.9 of that 50 equals the E from
And you
position?
knew that there was 0.9 because 10% was taken away.
Okay.
Okay. So another way of thinking about it is that the dissipated energy is 1/10 of the gravity energy.
Oh, my bad.
Okay. All right. I have been summoned elsewhere, but I will come. I don't know if I'll come back, but it seems like you're on the right track.
So we've gone over all the problems. Oh, hello.
All right. Sorry.
It's okay.
It's not always easy to interrupt the conversation I'm in.
No, it's
Tell me moon thing.
What's our question?
it's on number 9.
Yeah.
So we were wondering about like the like how to find the mass of the car. And
Well, you can't.
you can't.
It's not
So
possible.
then what equation should we look to like use?
Well, let's start off with a so if we look at this, what would you start off with? So you have your LOL diagram, right?
Yeah.
And then what the next step after the LOL diagram is to do what?
To write down the you mean like if it was like the whole LOL diagram? If we fill, or do you mean like doing L, then O, then L?
Well, you have an LOL diagram, hopefully.
Okay. Oh no, yeah. Okay, no, I get it. So we do that. Then would you want us to write down like a equation?
Yeah, that's
Okay.
the next step. So you have an LOL diagram.
Mhm.
And then the next step would be to write down the energy conservation equation.
Okay.
So let's do that.
All right. So it would be the gravity energy at A equals the kinetic energy at B plus the dissipated energy at B. Or would it be minus 10%?
Well, so you told me, is this just, don't think about the 10% yet. Is this statement that Max just made, is that a correct statement? Mason's nodding, Garrett's staring off into space, and Amaya is showing me her ceiling fixtures.
I think they get it.
Okay, I guess I have to assume that. All right, so then now how do you put the 10% into that equation?
Well, I said it was like you could subtract it because it's dissipated energy.
Okay, so you would suddenly change the plus into a minus?
But I mean, if it's taking like if the dissipated energy is taking away and you add it, isn't the same thing. If you subtract it, wouldn't you then be adding it? Because like it's like, think of it as a negative number. Like if you
Yeah.
subtract a negative number, you're adding it.
Okay.
Yeah, if I said EKB minus EDIS, that wouldn't make any sense,
Yeah.
right?
Okay. So like plus. That's a negative number, so it subtracts.
So, but I can replace EDIS with what?
10% of EKB.
10% of EG, not 10% of EKB. Well, yes, I could, but 10% of EG.
Okay.
Because that's what it's 10% of, right?
Yeah. All
right. So then, can we make a statement about EGA and EKB, right?
Could you just say that EGA is 90% of EKB?
No, that's not good. That's not good algebra.
Oh, okay. What'd you say, Garrett?
Wouldn't it be the other way around? It would be like, actually, no. Well, yeah. It would be EKB is equal to 0.9 EGA.
Okay, there we go. That's good algebra. Okay. So I can subtract a 10% EG from both sides. And that leaves me with 0.9 EGA is equal to EKB.
.9 EGA equals EKB. Okay.
Okay. So I've been saying all along that people need to put in as few numbers as possible, as late as possible, right? So, and this is a perfect example of why it is so much more powerful to use symbols as long as possible. So let's try that strategy and just put in symbols for the energies. So like what equations could we put in for those energies, but keep them all symbols? Don't put in numbers.
Okay, I think I kind of. So would you kind of combine the elastic energy equation and, or not the, would you combine the gravitational energy equation and the kinetic energy equation and then fill in from there?
Possibly. I'm not quite sure what you mean by combine, but why don't you try it out and we'll see if it looks good.
I mean, like if there wasn't the 0.9, if we know that and like gravitational energy equals kinetic energy, then couldn't you say that 10 newtons over kilograms times mass times height equals 1/2 mass times velocity squared?
Yep, you could. But now you can say 0.9 times 10 times mg.
Okay.
Times mh.
So we said that the gravity, so it'd be 0.9 and then 10 newtons over, it'd just be that equation.
Yeah.
Here's h. Then that equation equals 1/2 mass times velocity squared.
Okay. Now what happens?
We can just fill stuff in. For what we
know. No, don't fill stuff in.
Okay.
Look at that like an algebra student.
We can divide. Wait, if we divide the 1/2, do we have to divide the whole other side, or can we divide just one thing?
You've taken algebra, right, Max?
Yeah.
Okay.
Wait, let me move this a second. Hold on. Should I, or let me see your screen.
So we are trying to find velocity, right? So this is an algebra question. Find velocity. using this equation. So effectively, what I am saying is solve for V.
Solve for V. Okay.
So you have an equation, solve it for V.
So we divide out the other numbers and then just square root them.
Okay.
Okay.
Like, assuming people know how to do algebra.
Yeah. No, there's just like there's like a few things that are kind of like.
Somebody got kicked out. I gotta go help them.
Oh, okay.
I will be back.
All right.
All right, Andrew, I think it took me a second to notice that you were.
Yeah, I crashed.
Zoom doesn't like throw that in my face, unfortunately.
Oh yeah, I had to restart my computer, which I did, and
it happens at least once a class. So where
group 4, breakout room 4.
Okay.
Yeah. With Austin, it's the one with Austin, Sasha, yeah, June. Join button's not working.
Great.
Yes.
Oh no, I invited you to invite Andrew back in.
Oh.
Yeah.
Yeah. You're like, Andrew's missing. We need him.
Yeah.
All right. Let's discuss number 9 while we're here.
Okay.
Yes.
So I got or we all 9.49 meters per second.
And I need somebody, this is not something that you can just verbally talk through, at least not without driving yourself crazy.
Okay. For 9, basically, I knew that, so 90% of the original gravitational energy was going to equal the kinetic energy in position B, because 10% of it is dissipated. So basically that means that 0.9 times the formula for gravitational energy is equal to the formula for kinetic energy. And what I realized when I was solving that is that mass cancels, as you can see here. And when you just solve that algebraically, you should get velocity is 9.49 meters per second, approximately.
Okay. Anybody have any questions about that? What are some good takeaways from this problem? I mean, this problem I get more email about than any other problem. Right? So it's obviously tricky.
Well, you have to like remember like that the mass cancels out, because when I first was looking at this question, I was like, how am I gonna even figure out what the gravitational energy is, because I don't even know the mass or the velocity.
Right.
But it cancels out, so you have to think about that too.
Okay, so if you're in a situation where you don't know something, okay, put it in as a variable and keep going, seeing what happens. Right. Also, I have encouraged folks to always start with algebra. Okay, so start with this and then put in algebra variables before any numbers. Then solve that algebra before plugging in the numbers. Okay, if you do that, then you're much more likely to notice that things cancel. Okay. All right. Looks good. I'm going to check in with the last room here. Unless we have. Do you have a question, Sasha?
Oh no, I just said thank you.
Oh, you're welcome. All right. How do we do on number 9?
Okay. I was talking about it last night a little bit with Diana about it.
For number 9?
Yeah. Here, I can do a screen share. It's here.
Okay. So I like how you started off with an energy equation. That is going to be the beginning of like every problem after you do the LOLs. Okay. And then you said, oh, well, then that's 10% lost. Okay. So that's good. And then looks like you plugged in numbers for the mass. How did you handle not knowing the mass?
Just like, I think it was, I was sort of like talking about it. Like if you sort of do it, I think the mass cancels in the velocity equation.
Okay, so let's look at
exactly what I did.
So EK, right? So I'm going to take this right here. And I'm going to say 1/2 mv squared. That's the kinetic energy, and then that equals, right, 9/10, 90% of the gravitational energy, which is mgh. Right?
Yeah.
So then what happens to the m?
They cancel.
Cancels,
cancel. Okay. And the problem's trying to find the final velocity. So this is an algebra equation that I can then solve for v. And then plug in my numbers. And then I will get an answer for v.
I see.
Okay?
Yeah.
Which I think is what you did. It's just really messy and impossible to solve after this. Like, sorry, impossible to follow. Once I get to here, I can't follow it anymore.
Okay.
Okay?
Should redo that part.
All right, we're going to head back to the main room right now.
Yeah.
All right, so I think I was able to get around to everybody and discuss problem number 9. The main thing about problem number 9 is that you really, I mean, I've said this several times, but this is one of the first times that I've shown, not said. So probably I should just show. I mean, it's good storytelling to show, not tell, right? And I still think we're missing a couple people. There's always people who hang out in the breakout room until they get kicked out. Okay, so I've said several times that you need to stop using numbers, start using variables. Use algebraic symbols in your thinking. And this is why, number 9 is a big example of why. Because if you put in everything as a variable, you will quickly see that the mass cancels out. Okay, if you start using numbers, as I'll be honest, 95% of you do, then you write me emails about how I don't know what the mass is. Okay, so that's why you want to start using algebra if you're going to become a powerful STEM person. Okay, so next thing I want to go over really quickly is what power is. All right, so let's consider walking Here, I'll mute everybody. Consider walking up the stairs versus running up the stairs. If we think about these two different situations, both of them involve an object going from lower, closer to the Earth, to farther away from the Earth. And so that's a change in gravitational energy, all right? But both of these situations have the same change in gravitational energy. They're identical as far as changing energy is concerned. But we all know that running up the stairs is a little bit more difficult than walking up the stairs. So energy change doesn't really explain why that is. And so we need a new concept to explain why doing something quickly what's missing here is any sort of sense of time. Gravitational energy doesn't have any time aspect. So what's missing is a consideration of the time. So hence we introduce power. And power is the change in energy of a situation divided by the time that change took. Okay? So if I was to make an equation, it would be power is equal to the change in energy divided by the time it took. Right, so it's just a way of talking about. So running up the stairs takes more power than walking up the stairs does. I have to I have to do that change in energy quicker. All right, so the units of power are the joule per second. Okay, now we all know the physicists are lazy, so lazy physicists don't want to write joule per second. That's way too much writing, and so we use watts to mean joule per second, abbreviated W. Okay, so a watt is a joule per second. Now, if you've ever gone shopping for a light bulb or something like that, then they're often rated in watts. That's historical. It's actually changed. So they no longer actually have that many watts, but used to go back when I was a kid, and you go to the store and you'd buy a 60-watt light bulb. That literally meant that the bulb used 60 joules of energy every second. All right, but then they got rid of those light bulbs to help save the planet. And now the same amount of light can be given out of a 7-watt light bulb. But us old people can't learn how to shop differently, so we still go looking around the store for a 60-watt light bulb. So they're still labeled like 60-watt equivalent, even though they only use 7 watts. Okay, so you're going to need to know this in order to do your homework, which is to finish as much as you can at worksheet 5. Now, I am not going to grade worksheet 4 for a little while. We haven't had a chance to discuss number 10. So I am actually going to change the quality part grading for worksheet 4 to next week. Okay, so we'll start off next class on Thursday, finishing up worksheet 4 and then starting worksheet 5. But you need to do worksheet 5 in order for us to do that. All right. All right, thanks for staying a couple extra minutes with me. Thanks for waking up and coming to class. Have a great long weekend. I hope you do something that gets your mind off things or whatever. You know, just take care of yourselves.
Thank you, Dr. Schmidt. See ya.
Bye. Thank you, Dr. Schmidt.
Yeah.
Thank you. Thank you. Also, Dr. Schmidt.
Yeah.
I kind of have a question for.
No, you cut out there. You have a question about something.
Thank you, Dr. Schmidt. Surface is still lagging.
Oh, I'm sorry to hear
I've been
that.
trying to click the leave button. It's not working.
It's
but
not letting me
goodbye.
leave. I could probably kick you out if you would like.
Actually, you could. Except you might ban me. So
Yeah, no, we don't want to permaban you.
Okay, let's just see if it works. It's not working.
There we go.
It worked.
Are you also stuck, Alan? Or you have a question?
No, I just have a question.
Okay, let's let Kiko go first.
Yeah, because I'm. Should I?
Are you still there, Kiko?
Yeah, I am. Oh, I think I'm.
Yeah.
I kind of have a question. I know.
Kiko, try turning off your video. That might give us enough bandwidth.
Okay. Hello?
Yeah, I can, you're still sort of cutting out, but try. What's your question?
Okay. Yeah, I actually have my answer, but I'm not sure remember that.
Ah, this is frustrating. Can you try doing the chat?
Yeah, I will do that.
Okay, yeah, we're gonna do number 10 next class. Okay, so I'm not gonna grade this assignment until next week after we have a chance to go over number 10. Okay. Do you want me to look at it? Yeah, I'll look at it. So for number 10, so we're thinking about two different situations here. Position A, the item is sitting inside of the railgun. So it doesn't have any energy at that point.
Okay.
Okay, so it doesn't have any kinetic energy. And then the railgun pumps a whole bunch of energy into the system. And then we end up with some kinetic energy and some gravitational energy when it's orbiting above the moon.
Okay.
Okay.
Yeah.
And so then your gravitational energy looks good. Yep, so assuming you did your calculations correctly, that looks fine. The E means times 10 to.
Oh.
So that's the way your calculator side says times 10. So what you got was 1.605, right, times 10 to the 10th.
Oh, okay. I got you.
Okay?
Okay.
All right, like I said, we'll go over this one briefly at the start of next class.
Yep.
Okay?
Yep.
All right, Alan.
Yeah, I just have a quick question. On the you created my energy 3 worksheet thing. You put a comment at the bottom that said Also, energy not in the system shouldn't be in your L graph.
Mhm.
But what does that mean? Like in every problem, or just in the last problem?
Well, so the whole point of defining the system is that that's where we're keeping track of our the amount of energy that we have stored.
So
Okay.
wait, do you mean like in every problem, or just in the last
And
problem?
every problem.
So energy thermal should be empty in all of them?
No, because thermal energy, some people like to put in the system.
Oh, so I just either or put it in the system or just take it out, or?
Yeah. So you can put thermal energy in the system. So like number 5B here, right?
Yep.
You put thermal energy in the system. That's fine.
Okay.
Okay. So
If I
and
just do that a little bit like what is it? Ground. Does that work? If I
you can still just put it down here in the reservoir. That's fine.
What do you mean?
I mean, in this problem, you put it in the reservoir right here.
Yeah.
Right?
So should I take it out of the reservoir?
No, it's fine to put it there. You're just considering the reservoir to be part of the system.
Wait. So I'm confused. So what do you want me to do to change to fix?
And number 6.
No, like in all of them.
Oh,
Not
all of them are fine. In number 6, I don't know. Did you change something?
on 4A is the same thing. I have it in the reservoir, but I also have it in the L graph. Should I just take it out of the L graph completely?
No, it's fine the way it is. Don't worry about the thermal energy. Thermal energy is kind of a switch hitter. It's both inside the system and then also outside the system.
I'm confused now. So what am I doing wrong? I'm sorry.
Well, so for number 6, the energy leaving in this case is not going to the thermal reservoir. So originally you put it as going into the thermal reservoir.
Wait, number 6.
In number 6B. Right? It looks like you fixed it.
I just said energy out.
Yeah.
Right.
So that's completely different because it's going to the cord.
Oh, okay. So in like question 4, it's fine if the way it is.
Yes.
Oh, okay. So the reservoir is part of the system.
Yes. It's probably easiest to think about the reservoir as being part of the system.
I thought about what you were saying is that the reservoir was a part of the system. Like I thought that was like you're correct.
No, I'm saying the cord's not part of the system.
Okay.
And you were putting the energy into the reservoir, not the cord.
So that would be fine, just the way that is, right? Like I already put energy out and it's not in the graph anymore.
Yep.
Oh.
6B has been fixed.
Awesome.
So send me an email about it and I'll regrade it.
Awesome. Thank you, Mr. Schmidt.
No problem.
I'll see you on. Wait, we don't have class.
A week.
Oof.
I know.
Nice.
Yeah. Bye.